Good morning, everyone. And it is my immense pleasure to present a seminar in the International Commission on Planetary Atmospheres and their Evolution. So, as you all know, my name is Sefali Uttam, and I have recently completed my PhD from PRL India. And today I will be discussing about the Martian dust devil activities. So, let us start with the comparison between Earth and Mars to understand the difference between these planets. So, Mars is roughly half the size of Earth, which in turn reduces its gravity. So, the Martian gravity is approximately 0.38 times that of Earth. And due to this, we can understand that the atmosphere of Mars will be thin as when you compare it with Earth. So, Martian atmosphere is approximately 100 times thinner than that of Earth, due to which the average surface pressure on Mars remains around 6 hectopascal. Now, Mars is at around 1.5 AU distance from the sun, so it receives less solar radiation, which can be seen from the ratio of the solar constant for both planets. So, due to less solar radiation being received and thin atmosphere, the average surface temperature on Mars remains somewhere around 210 Kelvin. So this shows that though both planets experiences nearly same atmospheric processes, but the intensity of those will differ based on the atmospheric parameters. Now, Mars being farther away from Sun has a larger orbit to cover while revolving around the Sun. So, 1 year on Mars is approximately 2 times that on Earth. So, the figure here is an illustration of Martian orbit, which shows that the Mars revolves around the Sun in an elliptical orbit, in which it is closest to the Sun around southern summertime, which is extending from LS 270 degree to 0 degree. So it is this time of the Martian year when major dust activities are observed. So several observations of global scale temperature, all as recorded by instruments like TESS and THEMIS, also shows that southern summer is more intense as compared to the northern summer, like its counterpart. So a basic question always arises, that is dust always present in the Martian atmosphere? The figure here shows the longitude average TESS and THEMIS retrieved dust optical depth at 9.3 micron band as a function of solar longitude for southern subtropical region. So we can see from this figure that during the global dust storm of Martian year 25 and 28, the optical depth shows a sharp peak. So, whereas in every other year, the dust opacity reaches a maximum value of zero point 0.5 during the summer season, which is attributed to the occurrences of regional dust storms on Mars. But the background opacity of the atmosphere is always zero point 0.1, which proves that, that the atmosphere of Mars is always covered with dust. So, the dust is a fundamental component of the Martian atmosphere. This dust has an important feedback on the climate of Mars and impacts its thermal and dynamical state. It absorbs the incoming solar radiation and outgoing radiation from the surface and warms the atmosphere. And because the Martian atmosphere is so thin, even adding a small amount of dust greatly increases the amount of sunlight absorbed, which also affects the temperature, and in turn it affects the entire atmospheric circulation. So in a way it affects the temperature cycle of the Martian atmosphere. And this will have, obviously, if your temperature is being affected, then the dynamics of the atmosphere will also change. So it is important to study the processes by which dust can enter into the atmosphere. And one of the ways by which dust can enter into the atmosphere is by the generation of dust laden vortices, which are popularly known as dust devils. Now, this is a schematic of a convection generated vortex in the atmosphere. Now, a convection generally develops in the atmosphere due to solar heating, and this generates an instability due to which the hot air rises and the cold air rushes in to take its place. Now, these winds already have vorticity, and to conserve the angular momentum, the wind starts rotating, and due to this, a vortex is being formed. So when the vortex winds are strong enough, they lift dust particles in the nearby areas, and whatever like comes in their path, they just lifts all those dust and form a dust devil. Now there are several images of dust devil which are being taken until now, but then the first image of a dust devil was taken by a Viking orbiter, and the image here shows you a dust devil as observed by Mars Color Camera onboard MOM mission, which was a Martian orbiter mission by India. Now, another image here shows a moving dust devil as captured by a camera onboard Curiosity rover in the Gale crater. There are several studies done on dust devil characteristics on Mars, but it is still not well understood. So, in this seminar, I will be discussing our recent results from our analysis using data from Curiosity mission and our model which solved for the spatial distribution of dust concentration within a steady state Martian dust devil and the electric field generation within a steady state dust devil. Now, for the observational study of the convective vortices on Mars, we have used the meteorological data as recorded by REMS instrument onboard Curiosity rover. So, this is an image of a Curiosity rover which was carried to Mars as per the Mars Science Laboratory space mission. So this mission was launched by NASA in like 2011, and which successfully landed Curiosity rover in the Gale crater on August 2012. So the basic objectives of this mission was to investigate the Mars habitability and study its climate, and also collect data for human mission to Mars. So onboard Curiosity rover, there is a weather station named REMS, like a Rover Environmental Monitoring Station, which measures atmospheric humidity, pressure, temperature, wind speeds, and UV radiation levels. So it consists of two booms on the rover's neck, which and these booms carry sensors which records the air temperature, ground temperature, and wind data. And then on the rover back there is a UV sensor which consists of an array of detectors which are sensitive to specific frequencies of sunlight. So for the current study, we have used the pressure data and the UV data as measured during mission Sol 1019 to 1687, which covers the Martian Year 33 to search for the signatures of convective vortices. So this figure here shows the path traveled by the rover within the Gale crater in yellow. And during Martian Year 33, the rover has climbed up along the slopes of Aeolis Mons, and this can be seen as marked by a circle in white. So uh, we cover the time ranging from 8 LTST to 17 LTST on each mission Sol in our study. Now, the main signatures of a convective vortex are a drop in pressure, a rise in temperature, and changing wind speed and direction. Now, a temperature variation is very difficult to measure because it requires a good response, fast response time for the temperature sensor. And moreover, like during the previous missions to Mars, which it was been observed that it is not always that a pressure drop was accompanied by a rise in temperature, because it could not record such a fast change in temperature. Okay, so we generally don't we will not use a rise in temperature to detect the vortex. And also one of the REMS wind sensor was found to be partly damaged after MSL landing, and even after proper recalibration of the wind data, it was obtained for every 5 minutes. Now, for detecting a vortex based on wind data, we require data points which within a time scale of seconds, because dust devils itself sustains for around maximum 10 minutes on Mars. So we cannot use data of wind which is being given at every 5 minutes. So we cannot detect data. We cannot detect the vortex using this data. So we identify convective vortices by primarily searching for the transient pressure drops. So we use an algorithm to identify the vortices by detecting a sudden drop in pressure signal, whereas the dust devils are detected by a simultaneous drop in the UV flux. And apart from that, we have also determined the dust devil activity, which I will be like naming as DDA from now onwards, using the Mars WRF model to compare our result with the model out. So the image here shows the REMS measurement of pressure, air temperature, and UV intensity during a vortex event on mission Sol 1546 at the noon time. So as already stated, a vortex is identified by a drop in pressure, which you can see from the image in the left hand side. Since a vortex is formed due to heating of the surface, so whenever a vortex is formed, it will be accompanied by a rise in temperature. Hence, the image here shows that the air temperature is also increasing during the vortex event. And the figure in the right side shows a simultaneous drop in the UV flux. So generally, you will see a drop in UV flux for those vortices which pass between the rover and the direction of sun, so that at least they can cast a shadow on the sensor. Uh, Throughout my study, I classify only those vortices as dust devils which has casted a shadow on the UV sensor. Okay, so we have identified 611 vortices in 669 sols. The image here shows the number of detected vortices varying with the mission sols during each season on Mars in Martian year 33. So we can see from this image that during the local winter season, which extends from LS 90 to 180 degrees, the number of vortices are the least, whereas during the local summer season, which extends from like LS 270 to 360 degrees, the number of vortices are the maximum. So one of the reasons for this increased vortex activity during local summer season is the high solar insolation received during this time, which enhances the convective processes. Now, the figure here shows the cumulative magnitude distribution of the pressure drops and the corresponding power law fit slope. So, this study actually helps us to determine how many vortices at the given location will be capable of lifting dust. The magnitude of the power law fit in our study is 2.6. A higher value of power law slope means that the vortices with higher pressure drop uh, magnitudes will be less frequently formed as compared to their weaker counterparts. So, this means that the chances of dust devil generation will be reduced. The power law fit for Pathfinder mission is 1.75, whereas the power law fit for Phoenix mission is 2.36. Now, since the power law fit value is the maximum at the Curiosity site, hence it suggests a low abundance of stronger pressure drops events at the MSL location as compared to the Pathfinder and Phoenix sites. The reason for this can be attributed to the smaller boundary layer height at the Gale crater. Now, the height of the boundary layer at Gale crater is approximately varying between 3 to 5 kilometer, whereas it is around 4 kilometer at Phoenix landing site and 9 kilometer at the Pathfinder landing site. Now, since the height of the boundary layer determines the strength of the turbulence in the atmosphere, so if the turbulence is less, the chance of formation of dust devils also become less. Now, out of 611 vortices, only 63 vortices show a simultaneous drop in the UV flux. So, we have performed a seasonal study of the UV drops associated with the convective vortices and compared them to the dust devil activity output of the Mars WRF model, which we have used in this study. So the seasonal variation of dust devils were not studying using the data of the previous MSL mission years because of the lack of observation of such events. And but we observed that the number of UV drops detected is least during the local winter season. And the similar trend is seen in the dust devil activity, which is minimum during the same season. Generally, the number of events with UV attenuation and this strength increases as we move towards the local summer season. So, this may be due to stronger vortices forming at this time of the year, resulting in more dust lifting, or and the same trend is also seen from the model output of the dust devil activity. Now, the dust devil activity also depends on the sensible heat flux and the boundary layer height. So, during summer season, your heat flux increase, which in turn leads to the formation of a deeper boundary layer. So, in a way, dust devil activity should also increase during summer season, which explains our observation. Now, you can see the video over here, which shows a drone shot of a dust devil at Oregon on Earth. So we can see that a dust devil is roughly cylindrical in shape and carries most amount of dust in the lowest part. Another video here is captured by the navigation cameras on Perseverance rover, which shows these dust devils swirling across the Jezero crater on the 148th Martian sol of the mission. So what we can see that the dust devils look similar on both Earth and Mars, and also form under similar conditions, but they differ with each other in terms of intensity. That is, it differs with from each other in terms of like speed and dimensions of the dust devils and their dust content. So as mentioned earlier, the exact amount of dust injected into the atmosphere by dust devils, which will contribute to the total dust budget of the atmosphere, is not clearly known. So we have modeled the spatial distribution of dust concentration within a steady state Martian dust devil for the first time. So in our work, we take parameterized equations for the wind profile of the steady state dust devil as given by Vetistas et al. 1991, and um, we constrain these equations for the Martian atmospheric condition using the wind velocity outputs from a Martian mesoscale model, so that the dust devil has a threshold speed capable of lifting dust. Then we numerically solve the equations of motion for dust particles to determine their velocity inside the dust devil. We consider that the drag, lift, and gravity forces acting on the dust particles due to vortex winds. The drag force maintains the forward motion, whereas the lift force provides the vertical motion to the particles, which is then counterbalanced by the gravitational force. Then, consequently, we determine the dust distribution within the dust devil using the continuity equations. And we solve these equations in the cylindrical coordinate system, where we consider the height of the dust devil to be around 1 kilometer and the radius to be 10 meters. This figure here shows the variation of particle number density with the height of the dust devil for the two distances from the center of the vortex. This result is for the dust particles having a size of 1 micron. And we can see that the dust density decreases exponentially with height, implying that the major dust loading remains within the lower 10% of the vortex height. And since the dust devil raises most of the dust in the lower tens of meters, it forms a sand skirt, which is also observed for all the terrestrial dust devils. Like I have already shown you in the video earlier, that the major part of dust loading was in the bottom part of the dust devils, which is also known as sand skirt. So we can see that the dust concentration decreases with increasing height, which is due to a competing effect of gravity and a change in vertical wind speeds. And we can also see from this figure that the particle number density is more at the edge of the vortex, which is around 10 meters. So this is because within a vortex, the wind speed is the highest at the edge. So it will lead to more dust lifting and accumulation of the dust at that position. Now, the figure here shows the spatial distribution of dust concentration for four different sizes of dust particles having radius of 0.5, 1.8 and 2.5 microns. Now, since the typical radius of Martian dust varies between zero point 0.1 to 10 micron, we have performed a simulation for these four different sizes of particles. So we have chosen these size so as to like cover the entire gamma distribution of dust particles on Mars, which shows that the predominant radius of dust particle on Mars will be at around 0.5 micron. And we can see from this figure that the number density of larger size particles decreases sharply as we move higher. And this indicates that larger grains tends to be lifted up to lower heights. And so the larger size particles, and yeah, so it is lifted to lower heights. So the large the size of the particle, the smaller will be its number density. And it happens since the mass of larger particles are higher, and so the gravity will tend to pull it down more as compared to the lighter particles. And moreover, it is also easy for smaller particles to be entrained by the winds to higher heights and remain suspended in the air due to smaller mass. Now, we have compared our result with the observations too. So we obtain an exponential decrease in particle concentration with height, which is also observed for the dust devils on Earth as point out by a research of Luan et al. 2017. So we obtain a dust concentration of approximately 1400 particles per cc near the surface, which matches closely with the reported near surface dust concentration of a Martian dust devil, which is around 1500 particles per cc. And moreover, we obtain a dust flux of approximately 10 to the power minus 5 kg per meter square per second in our study, which matches well with the laboratory simulation results, which lies between 10 to the power minus 2 to 10 to the power minus 5 kg per meter square per second for a Martian dust devil. And another dust flux estimate is given by the observation of dust devils using high rise images, which estimates that it should lie somewhere between minus 3 to 10 to 10 to the power minus 3 to 10 to the power minus 7 kg per meter square per second. Now, let us discuss about the electric field which will be generated within a dust devil. The winds in the dust devils are strong enough to lift dust from the surface and distribute it throughout the spatial extent of the dust devil. In this process, the dust particle collides with each other and are known to generate and transfer electric charges by triboelectric mechanism. So this is a kind of contact electrification in which the dust particles get charged based on their size and composition. The larger and the heavier particles become positively charged, and the smaller and the lighter particles become negatively charged. As we have already seen, that the smaller particles tend to move higher and heavier particles remain downwards. So a charge separation occurs, which leads to the generation of an electric dipole. So this is in briefly what happens within a dust storm or a dust devil on Mars. Now there are several terrestrial observations of the electric field within dust devil, which shows that electric field can vary from a few kilovolt per meter to hundreds of kilovolt per meter on Earth. But this figure here shows the observation of the electric field within a dust devil during a field campaign in the West Saharan desert. It shows the positive correlation between the pressure drop and the generated electric field within the uh, dust devil. Now, the observations of electric field within dust devils are available only for Earth as of now. No rover or lander on Mars has recorded any direct measurement for the electric field within the dust devils. So but we can still estimate the strength of the electric field which can be generated within a Martian dust devil. So we consider an approach for estimating the charge exchange per collision between two particles based on its composition and size as per this equation, where delta phi is the difference between the surface triboelectric potential of the particles. The electric field developing within a dust devil can be calculated using the continuity equation, where the current density is dependent on the number of large and small particle concentration, which is n, charge on large and small particles, which is q, and vertical velocity of large and small particles, which is v, and the conductivity of the atmosphere, which is denoted as sigma. So we expect the overall charge in the devil to have a net value of 0 to maintain a charge neutrality. So hence the current um, yeah. So now putting everything together and solving them leads us to this analytical solution for the electric field within a steady state dust devil. So the figure here shows the variation of electric field with time in dusty and non-dusty scenario of Martian atmosphere. The magnitude of the conductivity of the atmosphere during dusty condition is approximately 2 orders less than that during the non-dusty scenario on Mars. So we have assumed the values of other variables which is there in this equation as per the Martian atmosphere, and draw this graph from the equation. So this figure suggests that the electric field buildup is stronger in the presence of dust in the atmosphere. And the reason for this lies in the fact that during the presence of dust, the conductivity of the atmosphere is like less. It's around 2 orders less as compared to non-dusty atmosphere. And even when a moderate electric field is developed in the Martian atmosphere, a substantial dissipation current will be generated, and this will increase exponentially with increasing electric field. So a significant significant competing dissipation current develops in the atmosphere, which reduces the electric field. Now, the electric field breakdown value for Martian lower atmosphere is reported to be around 20 kilovolt per meter. And we can see that in the initial 30 seconds, the electric field reaches the breakdown value in a dusty atmosphere, whereas it takes more than 100 seconds to reach the same in a non-dusty atmosphere. Thus, the chance of detecting a lightning inside a dust devil on Mars is higher if the atmosphere is covered with dust. Now, we also consider the effect of charge relaxation due to conduction in the atmosphere. So, by charge relaxation, I mean that the tendency of of the whole system to limit the growth of charge on the particles, and this will help them to reach the equilibrium. So in earlier analytical solution, we had not considered the that there is a we had considered that there is a constant rate of charging of dust present inside the dust devil, and we ignored the fact that the time scales for particle charge relaxation may be of the same order, or sometimes even exceed the current generated from collision between the particles. So this is now incorporated in the equation and solved to achieve this analytical solution. And we again take the same value for all the parameters which we had earlier taken and see the difference between the previous and current results. So we observe that due to charge relaxation, the growth of electric field is affected with a reduction in its maximum value for both dusty and non-dusty scenarios. In non-dusty scenario, the conductivity is high, which leads to a faster relaxation and transfer of charges among the particles, thus leading to a early saturation of the electric field. Whereas in the dusty scenario, yeah, so yeah, so mm, yeah, so in the non-dusty scenario, we have seen that it leads to an early saturation of the electric field, whereas in the dusty scenario, the atmospheric conductivity is lower, which leads to a higher time scale required for charge relaxation as compared to non-dusty scenario. Due to this, the charge relaxation becomes slow with time and makes electric field reach saturation late as compared to its non-dusty counterparts. So we can still see that the electric field will reach breakdown in a dusty scenario and will not reach a breakdown in a non-dusty scenario. So the analytical models discussed provides a useful understanding of the electric field generation within the dust devils in the Martian atmosphere. However, for a better insight of this phenomena, we perform a numerical simulation of the electric field generation within a finite sized dust devil in the Martian atmosphere. So the figure here shows a schematic diagram of our computational domain. We assume our system to be in a cylindrical coordinate system with a symmetry about the z-axis, and the dust devil is at the center of the domain. Which is modeled by a cylinder of radius r naught, which we have taken to be around 5 meters, and the outer region is modeled by a cylinder of radius 20 r naught, and the height of the dust devil is taken to be 100 meters. So we solve the following basic electrostatic equations to determine the electric field. So in earlier studies, an equal distribution of charge within the dust devils was assumed to solve for the electric field within the domain. Now, like what they did, that they assumed that the bottom half of the dust devil will be totally positively charged, and the upper half of the dust devil will be completely negatively charged. So they used to like take a fully dipole configuration. However, in real scenario, this is not the case, and the number density of particles decreases rapidly with altitude. And we have already seen from the from my earlier calculations that it decreases exponentially with height. So if the number density falls sharply, uh, then the number like number density of the larger particles falls sharply than the number density of smaller particles. So now this makes the larger particles to be dominant in the lower part of the dust devil, and the smaller particles will reach higher altitudes. But throughout the vertical axis, the total density of particles within the dust devil will also decrease with altitude. So the figure in the left hand side shows the charge density distribution within our calculation domain at 500 second. The color bar represents the magnitude of charge density. The figure here shows the positive charges are concentrated in the lower part of the dust devil and cover a smaller volume as compared to the negative charges. The charge density is also decreasing with altitude and reach a magnitude of like zero, specifying the effect of vertical exponential distribution of dust particles within a dust devil. Now, due to this configuration of charge density, the electric field is developed uh, in our calculation domain as shown in the figure on the right hand side. The figure shows electric field distribution within our calculation domain at 500 seconds, and the color bar represents the magnitude of electric field. So the maximum magnitude of the electric field within the dust devil in our simulation is near approximately 5.5 kilovolt per meter at 500 seconds. So the magnitude of the electric field within the dust devil develops in the same way as the charge density developed with time, and this magnitude is much like we know that the breakdown voltage on Mars is around 20 kilovolt per meter, and this is very below the breakdown limit of the electric field in the Martian atmosphere. So when we simulate so we can see that for a medium size normal size dust devil on Mars, it is tough for it to go in the to show lightning, whereas when we simulate the electric field in our domain with dipole charge density configuration, we obtain a maximum electric field to be around 20 kilovolt per meter. Now, like in real life scenario, a dipolar charge distribution cannot occur. So there will always be a decreasing distribution of particles in which equal vertical separation of charges cannot occur. So it is tough to reach breakdown within a dust devil on Mars. But once the size of the dust devil is increased, and we can expect an increase in the strength of the electric field generated within the dust devil. So we have actually drawn important conclusions on the characteristics of Martian dust devils in our study. So we have analyzed the meteorological observations made by Curiosity rover for Martian Year 33 and detected a total of 611 daytime convective vortices. And using the UV attenuation data, we have predicted the possibility of about 63 dust devil occurrences in Martian Year 33 at the Curiosity rover location. The observation and the Mars WRF model output shows the frequency of dust devils occurrences increases as we approach the local summer season. Then we have numerically solved the equations of motion and continuity equation for the dust particles to determine the dust velocity and their quantitative distribution inside the Martian dust devil. So our simulation indicates a maximum concentration of 1400 particles per cc near the surface and a dust flux of 5 into 10 to the power minus 5 kg per meter square per second, which is consistent with the observation. And we also find that the electric field reaches the breakdown value faster in a dusty scenario as compared to a non-dusty scenario. And a vertical exponential distribution of charged particles will lead to development of lower electric field than the dipolar configuration of charged particles. And in the Martian atmosphere, larger size dust devils can generate electric field within it, which can reach breakdown and cause lightning. Thank you.